So APT is the astronomer's proposal tool. It is the final step in the proposal planning process. And once you're done, you actually you go to the submission tab and you submit your program from here. Something to keep in mind also for JWST, for those of you who have previously used Hubble, there is no phase 2 for JWST. You have to basically have your observations fully set up and ready to go at the time of submission of your proposal. So there is a bit more legwork up front, and no phase 2, no official phase 2 period later on. But if your program is accepted, you will work with an instrument scientist to optimize your program, and you can make changes at that time. But everything should be pretty much ready to go at the time of submission. APT provides capabilities to create solar system targets and also special requirements specific to solar system bodies to help determine when exactly an observation should occur. And there's also a new capability to visualize the ephemeris of a target, which we'll see coming up soon. So I'm going to open APT and create a new JWST proposal. So up here in the top left, go to New JWST Proposal. And it'll take me to a front matter page. There we go. So here's the front matter where you provide title, abstract, things like that. Choose a default access period, exclusive access period, things like that. I'm not going to go too in detail on some of this front matter, and a lot of it is straightforward and self-explanatory. But I will show down here for the scientific category. So there is solar system astronomy is the first option here. So we can select that. And this makes sure that your program goes to the right panel, right? You don't want to select, if you have a solar system program, you don't want to select galaxies. I think they'll figure out that it's not an appropriate proposal and send it to the right panel, but somebody's going to get grumpy. There's no need to select an alternate category unless your observations cut across different fields, and then at that point it'll be up to the policy folks at Space Telescope to determine which panel your program goes to if you have solar system observations mixed with exoplanet observations, for instance. But for a pure solar system program, you only need to select this the primary category, and then provide 2 to 5 science keywords. So we have a spread here of different options: asteroids, comets, trans-Neptunian objects, outer planets, right? There are a lot of different options here. And that again helps identify appropriate reviewers to serve on the panel based on the specific topic included in your proposal. Once you're done filling out all the front matter, the next step is to work with moving targets themselves. So we go to in the tree here on the left, we go down to targets, and we can select new solar system target, button roughly in the middle of the page here. And we are able to generate our own targets now. Quickly looking here, there's a name in the proposal. So this is the internal name. This is what you provide for identification within the proposal while you're navigating through it. But in most cases, the name for the archive will be auto-populated, depending on the options selected below. And that can't be changed. That makes it easy for people to find find observations of that target at a later time in the archive. So you can't name it something weird so nobody ever finds it. If you're observing Io, it'll show up as Io in the archive, right? No getting around that. And then a description. There are a few different options here, basic things. Is it an asteroid, a ring, things like that. So there are 3 different types, or 3 different levels for defining your solar system target. To demonstrate all of them, let's actually create a target. Let's create the Pele volcano on Io, right? So we're talking about a feature on a satellite of a giant planet, right? So those are your 3 levels. So level 1, you end up with 3 different options: standard target, comet, or asteroid. We're going to select standard target here. And then from the standard target drop-down menu, we have all of the named objects in the solar system, or I guess not quite yet. We have all of the planets, even ones that we can't observe, as well as the sun, and then the dwarf planets. So in this case, let's select Jupiter, and we'll go back here. And you see in the summary, we now see Jupiter as level 1. Now I want to look at a feature on Io. So level 2, in this drop-down menu, we select standard target again. But I'll point out here that there is an option for satellite. We don't actually want that in this case. Io is a standard target under Jupiter, right? It's one of the named satellites of Jupiter, so it's considered a standard target as well. Satellite here is if it's not a named satellite, right? If it's recently discovered, it doesn't show up as a standard target, and you have to input the orbital parameters yourself. So to avoid having to do that, we select standard target, and we see this long list of named Jupiter satellites. Io, luckily, is right here at the top. So we select Io and return back to the target definition. So now I see level 1 Jupiter, level 2 Io. And then level 3, we now no longer see standard target is not an option anymore, right? There are no standard targets with respect to Io. So what we want to do is specify a position on Io. And we have 2 different ways of doing that. We can use the planetographic coordinates or planetocentric coordinates. So planetographic coordinates are more accurate. They take into account the oblateness of the object, right? This is obviously something important for Saturn, which has, is visually oblate. Whereas planetocentric assumes a spherical body. In a lot of cases, you're not going to lose any accuracy by choosing planetocentric, but if there is information on the oblateness, it's worth it to choose the planetographic. So we're going to do that here. That'll open a new definition here for specific determining a specific coordinate on Io. So in this case, we have 2 x's here. These are the 2 quantities that we actually have to fill in. The others are extra if you have more complex observation or something is changing on the surface of the object, or more specifically for maybe a cloud feature on Jupiter, right? You can specify how that cloud feature is moving over time, given a starting point. So, but for a volcano on Io, it's not moving with respect to the coordinate system, so we just have to supply the longitude and latitude. For the Pele volcano, we have 255.3 degrees and minus 18.7 degrees latitude. The red X's go away, and now we just need to fill in the name of the object in the proposal. So as I mentioned before, the archive name is now set to Io, and it can't be changed, right? It's grayed out box. I can't change it. But for the name in the proposal, I'm going to call it Pele Volcano Io. It's worth noting also that APT doesn't like spaces in names, so you can use dashes or underscores instead if you have multiple words for the name of the object in the proposal. And I guess we can fill in something here. Satellite or feature. There we go. So that's a feature on Io. So now we've fully defined our 3-level target here for a volcano on Io. So we actually started with the most complicated example possible using all 3 different levels. But there are some other options that are simpler and perhaps used more frequently for minor bodies. We'll close this We'll collapse that one and go back to solar system targets, click new solar system target. And in this case, we want to, at the level 1, we want to create an asteroid. So instead of standard target, we're now going to go to asteroid, and we get a lot of different entry fields here. But there's a very easy way to fill it all out. Right at the top here is a search box, and you can provide either the name of the object, the primary designation, the provisional designation, the NAIF ID, and use that information to talk to JPL Horizons and retrieve the information, retrieve the orbital element information for the object. So let's go with another object we talked about earlier. Let's type in Cheroklo, and we can either hit enter or click the magnifying glass button. It'll take a little bit of time to communicate with the JPL Horizons server, and it'll give you a list of objects based on what you've typed in. You can type in a partial name. You can type in the letter C and see all of the objects that have C in them, or provide more information in this case, and you only get one object showing up, which is Cheroklo. So we'll click OK. We now see it's populated the NAIF name, the NAIF ID, and if we want to retrieve the orbital elements, we just check this box right here. It'll say this will replace the orbital elements with updated values. This action is not undoable, which is a more complicated way of saying that you can go back and change the values later. We'll click OK here. It'll talk to Horizons again and populate all the fields with semi-major axis, eccentricity, etc. It'll give you the date of the Horizons solution for the orbit, as well as the date that you retrieved the information. So between the time that you submit a proposal and when the observations are executed could be a year or more. And during that time, a lot of your targets will have updated orbit solutions. So prior to execution, it's very heavily encouraged that you update the orbital elements. So all you have to do is click this button, update orbital elements. Obviously, nothing is going to change here. We just retrieve them. But prior to your observations running, you can simply click this, resubmit your APT file, and you'll have the most up-to-date orbital elements before your observation kicks off. So that's the full definition for Cheroklo, right? It's typing in the name, clicking 2 buttons, and you have the information you need. We'll give it a name and let's call it an asteroid. All right. So that's how to define an asteroid. But you'll notice that there was also in the level 1 dropdown, there's a comet type. So let's create another new solar system object. And in the level 1 dropdown, we'll select comet instead. Right. So the difference here, you have some different orbital elements. Right. Instead of semi-major axis, we have perihelion instead, for instance. So it provides a different set of orbital elements, and also in some cases, you want to have the non-gravitational parameters filled out. In a lot of cases, you have to put these in yourself. But for some targets, as we'll see here, if I type in Temple 1, right, the target of the Deep Impact mission, and I search for that, right, we have one object, Comet Temple 1, click OK. And I'll check the box, say yes, please retrieve these elements. It'll talk to Horizons for a little bit, and then fill in all the values. Right, so again, we have similar information here. Date retrieved shows up, but we also have the non-gravitational parameters input down here. Now, if you have a comet, for instance, that doesn't have pre-populated non-gravitational parameters, what you can do is uncheck the box up here, and all of these become editable now. Right, and you can provide source of orbital elements, wherever you got these from, but you can change values, things like that. Or check the box to have it retrieve all the default values again. We've now gone through how to set up using all 3 different level 1 types for different types of solar system targets. Now let's actually set up some observations, take a look at some of the special constraints you can apply. So create a new observation folder and take a look at the observation here. Let's use the IO target for this observation. Let's do a MIRI imaging observation. So the instrument, select MIRI, imaging, target, volcano target. We'll select some basic things here just for later. These are basic APT things, so I'm not going to go into too much detail about some of these options. All right, so that just makes the errors go away for now. And now we'll pop over to solar system constraints. So solar system target windows over here, which in the newer version of APT just says solar system. For IO in particular, because it's in a very busy system, right? You have Jupiter itself, you have the other Galilean satellites. You get a lot of default windows that say, separation of your target from Europa has to be larger than 10 arc seconds, or from Ganymede, Callisto, larger than 10 arc seconds. You don't want the other satellites to clobber your observation. You have the same thing for, you don't want Io to be behind Jupiter. You don't want your specific target to be on the other side of Io that you can't see. So those are set up at the top here. And then every single solar system observation has this default window, making sure that the observation is occurring when the target is moving slower than 75 milliarc seconds per second. Most people won't come up against this as an issue, but it is there as a default, not affecting the schedulability for most observations. And you'll notice that you cannot remove this one, right? You can remove some of these other default ones that are populated for IO, but you cannot remove the speed limit. Now, these aren't the only types of observation or type of constraints that you can have either. Let's add a new constraint. Specifically, let's say we want to observe the volcano during an eclipse, right? When Io is in Jupiter's shadow. So we can select New Eclipse Observing Window. And we get this pop-up menu with these different options. So we'll select, we want the observation to be within this window, right? So you can also choose not within to say, make sure it doesn't occur during an eclipse. We can select either penumbral or umbral. Let's choose penumbral for now. Completeness, full, the eclipsed object. So we don't want to select our target here. We want to actually select Io itself as the eclipse object, right? And the eclipsing object is Jupiter. So the standard targets are always available in these drop-down menus. And we want Io in particular because a feature on Io in eclipse window isn't valid for a feature. It's valid for a body, but not a specific spot on that body. We'll get an error, like an error unschedulable visit if we choose the target itself. And of course, the observer here is JWST, though you can choose any standard target here as well. So we click OK. We now have this added constraint, which will shrink the window even further. So definitely be careful about the constraints you add, because it will affect schedulability. But now we're saying we want to make sure that we observe when Io is away from all of its Galilean satellite friends, when we can see the volcano, and when Io is in eclipse. So probably a very small window in this particular example. Also mention some of the other options here. So you can choose, you can specify based on a distance, right? So this is distance from the sun, for instance. or distance from this is a physical distance, right? Whereas separation is angular distance on the sky, right? You want to make sure that you observe when a satellite is a certain distance away from its giant planet. You can specify when an object is moving at a particular rate, when it's a certain distance away from the galactic plane, when it's a certain size. There are a few that provide roughly the same kind of information depending on the target, right? For a tidally locked satellite, central meridian longitude gives you the same thing as an orbital longitude, right? That's the difference between where it is on its orbit and where, what the rotation phase is. So there are a lot of different options for setting up your observations to make sure they occur at the right time. I encourage you also to look at the documentation to look at differences, for instance, between transits, occultations, eclipses. There are some nuances to how some of these work, right? So a transit is when the transit window starts when the transiting object is fully on the transited object, for instance. An occultation occurs when the limbs of the two objects touch, for instance. So there's some slight nuances there, and are worth further investigation if you're interested in those kind of constraints. And now, can I throw it over to you, Ian, to take a look at the ephemeris capability?
All right, so this is an example of a program. This happens to be my program from Cycle 3. Brian's also a co-I, as you can see here. So the 3 targets here were entered following the same process that Brian outlined using the Horizons query. These happen to be 3 Kuiper Belt objects. So these are point sources. And the observing strategy was to use NIRSpec IFU. We'll get into setting up observations later. But what we want to share here is that there's this new capability in this latest version of the APT. So I'm using 2024.5.2. Ingested the targets here. So the first step is to go to the observation page here and select Generate New Ephemeris. So you click this, and it pops up this little window that allows you to put in start and end dates. So what are the start and end dates? For that, we want to go to the visit planner. So here's the visit planner for this particular observation, observation 2. And you can hover over this block, which shows you the dates within the dates for which this object is observable. So you can see here it's from December 6th to 23rd of January of the next year. So keeping that in mind, we go back to the previous page that we were on. Oops, here. And I think I forgot the dates already, but we were just going to put, let's do January of 2025 to 10th of January 2025. Right? Those are dates that were in that range. And you can choose your step size, do 1 day. Right, and once we have that, we click generate, and it will take a sec. It's essentially requerying Horizons as well as a J2ST ephemeris and generating the information. All right, so click this, you have an ephemeris table. So we have a step size of 1 day. This tells us the RA and DEC as well as the heliocentric distance of this object on those days. All right, so the next step is to click View in Aladdin. All right. So this works, should show field of view on load DSS. All right. So you can see here that here is the fields of view of all of JWC's instruments. This is a NIRSpec observation. So this footprint here is the NIRSpec detectors. So being an IFU observation, the actual aperture of the IFU is very, very small. So to really see where the aperture is, So you can do this. We had to zoom in very, very close. And there it is. So it's a 30 by 30 pixel aperture. And you can see all the slices and also the different footprints of the aperture for the dithers. So in this case, there's 4 dithers. So the entire the pointing is shifting between the dithers, and you can see that this object is nice and centered in all the dithers. All right, so this is the other one of the other objects. So this is the first target. So you can see here there's a point for every day within the specified range. So I gave a range, a window. In this case, this is the full observability window for this target. And you can see here, this is the center of that range. And so you can see the motion of the object on the sky plane. And this is sort of the very similar thing as I showed before. You see the footprints of all the instruments. So based on the observation that you set up, it will center the ephemeris to align with the aperture of that corresponding observing mode. In this case, this is NIRSpec IFU. So the center is the aperture for the NIRSpec IFU, which is right here. So this is useful in case you want to see whether or not there's a nearby source. So you can imagine if you go to this date here, there's a pretty bright star here. So you can imagine that if your observation is scheduled very, very close to this point in its on-sky track, you could potentially have some issues with contamination from scattered light, or perhaps even as a source within the aperture. So this is really just a sanity check to make sure that your moving object track does not coincide with any very bright sources in the background.